Swayam Prabha. Digital India. Educated India.
At this problem, so let's take a look at this one. So we had looked at this problem before. We had a beam AB, some uniformly distributed load. You had a point load over here, which you remember when we solved using the method of sections. We have looked at it using the method of sections. So we had replaced this 10 kips, this is in kilopounds, 10 kips with the equivalent 10 kips as slightly shifted, and with a equivalent moment. This 20 kip feet is 10 times 20. So you're essentially this sort of a wedge that you have, and this load which is acting at the end of that wedge, you have transferred that same effect to the beam. So now that you are having to deal with just the beam itself. Now we had looked into this problem previously. So if you just quickly go back, so this is how we had solved it using the method of sections. So in the method of sections, we have taken a section here, like wherever the discontinuities are, we have or the loads are uniformly distributed loads are. So we have one section over here, second section here, third section over here. For each of these sections 1, 2 and 3, we had written out those equations and then found the shear force diagram and the bending moment diagram. Now this problem also gives you a hint at how complicated things can get when you try to have different sections and write the equation. So let's see that whether using the relationships between the bending moment, shear force and the loads is going to make our life easy. So for this problem, since it has all the types of loads, I'm going to write out the basic relationships again, so that we are all on the same page. So if we have to just quickly write the relationships down, so for the first relationship that was there was my dv dx is negative of wx. Now always remember, this negative sign is because w was acting vertically down. If it was acting vertically up, for example, if this load was pointing in the upwards, this would be a positive sign. So keep that in mind. And this also leads to that other relationship, that your between 2 points vd minus vc is negative of the area of the loading diagram, right? And the second relationship was dm dx was equals to v, and that also leads to a similar relationship as before. When you compare it with the loading, that you have md minus mc was the area of the shear force diagram. Now between those 2 points, so the area of the loading diagram, you must remember this is between c and d, and this is also the between c and d, because you're calculating the difference of the shears and the moment between those points. So between c and d. The third and the fourth one were because of the point load. So these two were for the distributed load, this one is for the point load. The third one was for the point load, where if you recall that we had that small element, and I'm going to just mark the force on top of this one with a force P. And if you had on the either side, you had the this shear and this shear over here. So this is say V, and this is V plus V1, and you had the moments. If this was M, this was M plus M1. What we found in this one, that your V1 was equals to minus P. So that meant that your shear was undergoing a jump. The shear undergoes a jump, right? And our m1 was equals to 0. So no change in moment when you have a point load. And lastly, we had our relationship number 4. The relationship number 4 was as a consequence of the point moment. So if I take a similar element again, and if you have a point moment on top, and in this point moment, suppose again you have the V, you have the M, you have the V plus V1, M plus M1. So in this one, what we had seen, that your M1 was, and suppose the value of this point moment is M0, some value. So m1 becomes equals to minus m naught. It is important to note that you can easily derive it, but just to make things quicker in your head, it's just you have to keep a note that the m naught here was marked anti-clockwise. As a consequence of it, the positive moment comes out as the negative m naught over here. And also for this one, your v1 was equals to 0, so no change in shear. So the first relationship means that your moment jumps. Now this is important it was important to write all of these, because the loading that you have over here, it sort of has all these types of loads. So here I have, as I said, I have done the equivalent of equivalent beam in with the equivalent loads. Now I'm going to draw the shear force diagram for this one and the bending moment diagram here. So let's go ahead and draw the shear force diagram first, and you will see how easy it becomes to draw using these relationships compared to the method of sections that we had looked at. Okay, so let's draw the shear force diagram. So let me put a divider line over here. Okay, so for the shear force diagram, so you see we have the distributed load here, we have a point load over here, and the distributed load magnitude over here is 3 per feet. I'm not marking the distance to make the figure messy. You have the distances over here. Okay, so when we are dealing with the shear force, essentially we have one relationship here. This is relationship 1, relationship 3. So let's see which one to make use of. So first you have this uniformly distributed load which is acting at this particular point. So from A to C, so let me go ahead and maybe draw my guidelines as well to help me draw neat shear force diagrams and bending moment diagrams. So one guideline at A. So wherever again you are having the discontinuities or the load ends or the load begins, around those points. So I have these A, B, C and D. Right. So again, focusing on the shear force diagram, I have, this is my A, this is C, this is my point D, and lastly I have this point B over here. So from A to C, I have these 3 kip feet. So let's just go ahead and write the relationship that we have. We have dv dx equals to minus of wx. Now here it is a constant, so my w of x is degree 0. So that tells me that from A to C, my v will be a degree 1, so it will be a linear line. Also intuitively I can tell that since it is a cantilever, here is a free end and there is no point load or no concentrated moment in this particular point. What we get essentially is that at this particular point my shear force will be 0. So I am starting from 0 over here, then I will have a linear line. Right now, also another thing to note, that whether it will be on the upside over here or the downside over here, so that will be dictated by the slope. And if you remember, so dv dx equals to the negative of this one over here, of the load at that particular point where you are computing the slope. So at here you see it is going to be dv dx will be minus 3, because the loading is minus 3. This is the loading minus 3, so it is going to be a downward trend, a downward linear line. So let's just go ahead and mark that one. So what we have is maybe from here to here, right, something like this, A to C, because I'm only drawing up to C because my uniformly distributed load is only up to C. And what is going to be the value of C that I can find from this relationship over here? So let me go ahead and just write that. So we have your let me just write it here. We have VC minus VA will be negative of the loading diagram between these 2 points, and that is just a 3 times this distance. So what is a rectangular patch, so is equal to 3 times 8. Now VA I know is 0, so your VC becomes equals to 24 kips, right? So this point here is 24, sorry, it will be a negative 24, minus 3 minus, yeah, because it's the negative of the area of the loading diagram. So this guy over here is a negative 24. I'm writing in the bottom half plane, so I'm not marking the negative sign. Now from C to D over here, from C to D, there is no load. No load means that, if the load is there is no distributed load, no point load, completely non-existence. So the shear force is going to be constant, because if you put a 0 over here, there is no distributed load or a point load to cause a jump. So you have a 0 load, so that means your V must be a constant. So from here, from C to D, I'm going to continue with a constant value of -24, right? Okay, now comes an interesting juncture over here, that at this particular point, at D over here, I have a point load, right? So the point load, what will the point load do? It will cause a jump. See over here, the point load then is vertically down, you have a negative increase, so you have a minus P, extra minus P. So this was V just to the left, and just to the right it becomes V plus V1, where V1, if the load is down, it is minus P, so it is going to be 24 minus, so it will be minus 24 minus of this 10 kips which is acting over here. So that will take me to a jump, so that will go further down over here, so that will go to maybe this particular point, so that will be minus 34. Very interesting, right? Now, as you can see here, in addition to the point load, I have a point moment, but I know that when I have a point moment, any point moment over here, there is no change in shear, so the only jump here is going to be caused by this point load, right? Now again, coming to the last part, from D to B, I do not have any load, no concentrated load, no distributed load. The shear force is going to remain a constant. Here I have a constant over here, and this goes and joins, right? So my whole shear force diagram is a negative shear force. I hope this was clear. So you see how easily we derive the shear force diagram, and if you just compare it with what we got over here, it's the exact same thing. But here to derive this, I had to write the equations for the different points, and the problem gets more complicated if you have more number of sections that you have to draw, if you have more number of loading. So now that our shear force diagram is done, let's go ahead and do the bending moment diagram. So let me put a divider line here. So next I'm going to go and derive the bending moment diagram. So this is my diagram for the BMD, right? Again, from plain and simple intuition, this is a free end with no externally applied moment, no externally applied concentrated load. So here the bending moment is going to be 0. So let me mark those points A, C, D and B. So at A, I'm going to have a 0 bending moment at this point over here. Now the question is that how from A to C it is going to vary over here. Now from, again, let's quickly write the relationship. We have dm dx equals to V over here, right? So that means that the slope at this particular point over here is going to be the value of the slope over here. So if this at particular point is going to be the value of the shear over here, the slope here dm dx at x equals to A is going to be the value of the shear at A. So value of the shear at A is 0. So here my bending moment diagram will have a 0 slope, right? Now let's try to find how the variation is going to be. So from A to C, so let's say from A to C, I have my V is a linear. So V is linear. So that means, so from A to C, V is degree 1. So that kind tells you that your moment, if you integrate this one over here, will be quadratic, right? So that means it's a quadratic. So if this is quadratic and I have a 0 slope over here, and what is going to be the slope at C? So that from A to C, the variation is quadratic, with the starting point at A, the slope as 0, and at C, the slope is going to be a negative 24. So it is going to be a what kind of a curve? Concave up or concave down? It's going to be a concave up curve. So at C, and also let's find the value of the moment at C. So how do we find that? We have MC minus MA. Right, this is from this relationship over here, that MC minus MA will be the area of the shear force diagram between these 2 points. So the area of the shear force diagram is this guy over here. So it is going to be equal to half. So it's a triangle, as you can see. So half times this distance 8 times the value of the shear force, that is minus 24. So that gives you minus 96 kip feet, right? So it is going to be at C, I am going to have a minus 96 over here. So let me maybe this particular point. So from here to here, I will have a quadratic variation. So let's just go ahead and draw that. And at this point, as we investigated that this slope, so let's just write the slope here. So here slope equals to 0, and this slope is minus 24. So we have reached the point C. Next we have to go from C to D. So if we have to go a bit further, so from C to D over here, you see the shear force is a constant line. So your V is 0, so that means your M must be the integral of that one must be a degree 1, so it will be a linear variation. And what is, so from C to D I will have a linear variation with the starting slope is the same, because this point there is nothing else, because the slope has to be this value of the shear force. Our starting slope is the same. So let's find the value of the moment at D. So how do I find that? So I have MD minus MC must be equals to the area of the shear force diagram between those 2 points, and that is this 24 times this ordinate. So sorry, this ordinate is 24 times this distance, so it is going to be minus of 24 times 3, that is minus 72. And at C I know the value is already 24 over here, right? Oh, I did not mark this one. So this one not 24, it will be minus 96. So let me mark this one, minus of 96, right? So MD minus MC is minus of negative of 72 over here. So let's just go ahead and find out what is going to be MC. So MD will be minus 72 plus MC, and MC itself is a negative 96, so minus 72 minus 96, that will give me a minus of 168. Again, keep it, right? So here I am going to have a linear, and the variation is linear as we pointed this out over here. So it is going to have a linear variation starting with the same slope, and the value is going to go to minus 168. So here it is 168 negative, right? Oh, sorry, I wrote the negative over here. If you are drawing in the bottom half plane, you need not have that. So it will be a minus 168 at this particular point. Now this one I have over here, and then so at this point D that you see over here, the issue is at D I have a concentrated moment, right, of this 20 kip feet that you see over here. So now the question is that how this moment is going to change. So for that you need to refer to this relationship 4. As you see here, when I had this kind of a moment, so the bending moment on the right hand side was reducing further by a minus m naught, right? But here the applied moment over here is clockwise, here it was anti-clockwise. So here I am going to have at this point D over here just to the right. So probably it's a better idea to write MD as maybe MD minus. Why? Because this is just to the left of D, right? So let's just mark it just when you have not made that concentrated moment, just to left of D, and just to the right of D, that is after you have made this concentrated moment. How does that change? So MD plus will be what was just to the left. Remember, this is going to be M, this is M plus F1. So this one was just to the left of that one, so which is 168. It is going to be negative of 168, and then plus M1, where my M1 is going to be a positive 20, because here when it was anti-clockwise it was a negative M0, so it is going to be a positive, so it is going to be minus 168 plus 20 over here. So that is minus 148. So here you are going to have a jump, right, in the upward direction. So it is a 148, a negative 148 over here. Again, I'm drawing in the bottom half plane. I am not marking the negative sign. If you want, if you are comfortable with it, and if you want to do it, you can mark the negative sign. You know, it's one and the same. What I try to do after I finish my diagram, I put a negative sign or a positive sign, and that takes care of, you know, what is positive and negative. So okay, anyway, so we have a, you know, at this particular point, just to the right of that, I have found a negative 148. Now the last bit what is remaining is from D to B over here. So let's just go ahead and, you know, write that as well, that from D to B at this particular region, my shear is a degree 0, because it's a constant line. So V is, you know, degree 0, so M must be linear, right? So you will have a linear variation. What is going to be the value? Let's try to find that out. So we have MB minus MD. So since I am going from here to here, the last encountered moment is that MD plus, which is just to the right of this section. So this is 148, right? So let me just go ahead and mark that MD plus. Let me write that a bit more clearly, right, is equal to the area of the shear force diagram between these points. So that is, you know, 34 times 34 times this distance, which is 3 plus 2 5, going to be minus of 34 times 5, and if you compute that, you will get MB is minus 34 times 5 plus of MD plus, so plus minus 148. Now if you compute that, now let's do the quick calculation. 34 times 5, you get a negative of 318. You get minus 318 hip feet. So from D to B, you have a linear variation, and the value at B is negative 318. So let's just, you know, mark that one, or maybe let's just draw the line, because it's a linear variation over here. And what will be the slope over here? The slope over here is going to be this one, 34. So this line will not be parallel to this one, because here the slope was negative 24, here the slope will be negative of 34. So at this point you have a minus 318 feet. And as is customary, we go ahead and draw this line. So you see it's actually quite pleasing to solve problems using the relationship. You get a very clear idea, a very nice transition, how it varies from one region to another. So my whole bending moment diagram is also a negative diagram. Now, as I said, you can mark the negatives or you can leave it, that's fine, as long as you're writing its negative. If you write the negative here, I know that you mean that all the values below that horizontal line of the beam is a negative value over here. So and let's compare of what we got. So let's just maybe write these ones. So this is quadratic, this is linear, this is also linear, and this is the place where you had the jump. So I hope this was clear. So let's just quickly compare with what we had got. See, this essentially same thing: 96, 168, 148, 318, quadratic, linear, and this is what we had as well: 96, 168, 148, 318, and it's a linear. So again, sorry, this should not be there if I'm working in the bottom half plane. Okay, so I hope this overall, problem example was clear to you. Try to do it once using the method of sections and using the relationship, and you will get an idea.